Okay, greetings everybody. We're going to be switching gears a little bit. We just finished up with the EM algorithm. We can do Q&As on that if it's still a little bit unclear. I did get a good question over email asking me what form of inference does this fall into, EM. And it depends on what you're applying it to. So if you're applying it to a posterior distribution, it's obviously Bayesian. What are you getting out of it? You're getting the math estimator after you marginalize out all the other parameters. And so that's an interesting technique to maximize something and marginalize over something else. The idea is you want your best guess at the thing that you're interested in talking about. So you're called that theta. The parameters underlying the mixture components. But there were things that you didn't want to know about. And so we just average away those things. I would always argue that that averaging sort of technique, that very Bayesian thing, is a good thing to do. When you average, you reduce variances. If you apply it to a likelihood function, that integration step, a Bayesian would argue that you're integrating the likelihood over psi, the unknown stuff, and you're using a uniform prior. So a Bayesian would argue you don't get to integrate across likelihoods until you upgrade something to a measure. And so they would argue, and there's a lot of arguments out there, that EM, when maximizing theta in the likelihood function, you're still treating the psi as Bayesian, you just didn't state your uniform prior. What Sierra may not have shown you is that if you wanted to, when you're trying to come up with the component labels, you could end up using a non-uniform prior. So let me give an example. So imagine you're trying to classify spam or not spam. And you knew something a priori, how many spams you expect to see. Is it very dense or is it very sparse? And so your spam filters kind of tune that. So they change the weights, you might say, i.e. change the prior. So if you do that explicitly, it's almost like you're absolutely a Bayesian on that step. But it's kind of a hybrid technique, I would say. There's a lot of papers out there that say EM is Bayes, and then there's a lot of responders to that say, not so fast. I'll integrate over my likelihoods and I don't need your permission slip. But they won't say what it is. The machine learners don't care. They just say, I just do this stuff, there's weights, call it whatever you want. So a lot of it is semantics. Depends on who you're talking to. When you're talking to me, I say that part of it is Bayesian. And part of it might not be Bayesian depending on which function you plugged into that to build your Q. So if you plugged in the posterior, you're kind of a full-blown Bayesian. There are alternative algorithms. So you could do the whole thing as an MCMC and get the joint posterior of the missing labels and the parameter sets. And that would kind of turn you into the full-blown Bayesian. It's a question of what do you want to do with those. I teach that in my base class. So for the other side to that algorithm. It's kind of interesting when you know both of them and you can compare and you can see what's similar and what's slightly different. So give it another semester and I'll teach you all about the full-blown Bayesian answer. Okay, I want to switch gears and just do some math. This is extremely important. Everybody uses this. It doesn't matter how you construct your estimators. This is useful. If you're a Bayesian, an MLEer, some sort of penalized MLEer, i.e. a Bayesian. If you like MOM estimators, however you get your estimates, this applies. So this is valid theory. So let me just make a quick announcement. And the midterm will be out on April 17th or 18th. This is a Saturday right here. It doesn't really matter when I send out a midterm if I say you have a week to complete it or a couple days to complete it. So I still intend to hold class on the 17th, so you're really looking right here. So I wrote that in on the web page that I'll be issuing a midterm on the 18th. So study up, try to study all this stuff. The format's going to change a little bit, and after I write the exam this weekend, I'll know exactly how the format has changed. So I'm working through a lot of issues. There's a lot of constraints, and I'm trying to dynamically figure out what the solution is to giving you a useful midterm. So i.e. I can see where you guys are at, and you can see where you're at. That's the goal. Okay, let's get on with it. So Cramer-Rao is this very useful thing that we want to talk about. So this is a lower bound. It establishes a lower bound. So let's just set the problem up. Same problem that we always see. Xi's come from some distribution, and I get a collection of n data points. I will point out that everything we're going to do today holds in general, and it doesn't need to be IID. So there could be dependence in this sampling mechanism. So everything I say today is general. And there are IID forms that might simplify a little bit of the math for you. My notation is that Wx is an estimator for theta. Okay, so it's supposed to be estimating theta. Cramer-Rao establishes a lower bound on how small the variance can be on an estimator. Okay, so it makes this statement about how small that thing can be. Sometimes this bound is attainable. A lot of times we can actually get equality. That there is an estimator out there that attains this lower bound. So let me be real clear. Wx is some arbitrary estimator. And I want to know, out of these collection of arbitrary estimators, how small the variance can be. So this is going to help us to figure out what the best estimators are. And so if there's an estimator out there that attains the lower bound, what we've proved is that there's no other estimator with a lower variance. So let me say this again. This is useful if we can attain. There's another word called obtain, and you can use it right here as well, but the book has a theory called the Attainment Theory, and it tells you the conditions and when you can actually attain this. And so, Sierra is giving me an indication that we're having a tornado warning right now, which is fascinating. I'm going to try to carry on as though the loudspeakers aren't blasting away right now, and Sierra will tell us if we're safe. Okay, so this is useful, this bound that we're going to establish, and I'll point out there are assumptions. I don't want to cloud the conversation yet. Sometimes this does not apply, and I'll tell you what the assumptions are. But this is useful if we can attain the lower bound. And I'll explain that just a little bit more. If we have an estimator that attains the lower bound, it's best, it's optimal. So it's the best one you can find. So that's kind of a nice thing. So you might be pondering, if you were just developing estimators, is there an estimator out there that's better than yours? And you would need to do an infinite number of comparisons to find out something that's impossible to do. So this theory tells us whether or not we can do any better than what we've just found. So we'll have estimators, we'll compute this lower bound. If our variance matches this lower bound, I know I cannot go lower. Now there's a caveat to all of this, and it's the numerator condition. This right here is a function of theta, so an expectation of the estimator. This is just something we can compute. So we can compute that. There's no thetas in here, but after I take the expectation, there's thetas there. So just be real clear about which expectation this is. This is with respect to the sampling distribution. So this would be the whole data set all at once. This is a function of theta right here. And so this is stipulating a bias condition on this estimator right here. So if this expectation were theta, this would be saying for the class of unbiased estimators, i.e. expectation of Wx is equal to theta, those are unbiased estimators, this tells us how low the variance can go. So most of you will know there's a trade-off between those two things. If I increase my bias, I'll often decrease my variance. And so, and both of those things are important. And so this is stipulating how biased everything is. So the expectation of Wx, how far that deviates from theta, is the bias. And so this is predetermining a variance bound with a predetermined level of bias. So I could figure out if this numerator, this thing was equal to theta, the derivative with respect to theta is 1. 1 squared is still 1. The variance is determined by this denominator, the lower bound on it. And so, if, however, I were willing to incur a little bit of bias, this was some function of theta but not precisely theta, then this would determine the lower bound on the variance for that level of bias. Okay, so some people like unbiased estimators and they can come up with a lower bound on variance for those using this. So there's a little bit of complexity here. There are assumptions for whether or not this is a true mathematical statement. So as written on the board, this might not be true. So we're going to need some special assumptions for this to be true. Let me tell you what the assumptions are. So these assumptions here. It's pretty simple. So assumption 1, assumption 2. You write down the obvious assumption first. Variance of my estimator is finite. So it exists. So that's the obvious one. I want to think about this thing, but I want to think about something that actually exists in the first place. Okay. Obvious, but important to state. The second one is a statement about how I can exchange derivatives and integrations. So it says this. So that the derivative of the expectation, and I'll try to match the one they did in the book. Okay. This is the way they write this in the book. Is going to be equal to the integral of the derivative Wx fx given theta. The book writes this just slightly different. They bring this thing over here. This is an integration over x. So there's two operations that are happening. There's an operation on x, and there's an operation on theta. So this is a statement. This equality is true. There's only one thing I need to actually hold. It means that I can actually back, not this derivative just over that. This is not a function of theta, so there's no problem there. Not a function of theta. Don't be confused. The expectation is a function of theta. The thing itself is not a function of theta. It's an estimator. If you have theta in there, I can't use it to estimate theta because I need to know it. So this is a statement about this derivative right here being able to swing around the integration. So if you just think about what this is, right here, this is just the expectation or this expectation of Wx is just Wx, Fx, theta, dx. That's what that thing is. And so for this to be true, it just means that I'm able to slide this derivative through the integration operator. So that's called Fubini's theorem. Fubini's is a set of conditions that have to be true for this to be true in general. So it talks about what needs to be true about this operator and the stuff inside the integrand. And if you take a measure theory class, they'll run you through that. But saying that, we can always check if this is true. Is the left side equal to the right-hand side? I will warn you that there's some obvious stuff that can happen that if your parameter lives on the boundary of your set, theta will wind up on the bounds of your integration. And if that is true, you will not be able to slide this derivative operator over the integral side. And so for problems where the parameter of interest lives on the boundary, i.e. that parameter appears in the integration operator, you will not be able to slide the derivative through. So that's a case where Cramer-Rao says nothing. It's not useful theory because the assumption doesn't hold. It doesn't mean that there's not a lower bound on the variance of your estimators. It just means Cramer-Rao can't establish it for you. Can't say anything about it. So if your parameter lives on the boundary of the space, none of this applies. So I'll just give you a heads up. Very common for me to ask on qualifying exams and finals. I'll give some problem, ask a whole bunch of stuff about it, and I'll ask, how does Cramer-Rao apply to this problem? And people will work out Cramer-Rao, and they'll do all the math, and they'll spend a whole bunch of time doing this, and then they'll make a statement. And the answer would have been, it doesn't say anything. Don't do any math. So it doesn't actually establish a lower bound. So the assumption that needs to hold is this, Fubini's. I need to be able to fly the derivative sign over the integration operator. Okay, so pretty easy. Yes?
I just got an email that the tornado touched down near Mountain Lake and it's headed towards BT.
Interesting, thank you.
I'm going to log off for now because the internet connection in my basement is pretty bad.
Okay, you guys be safe and do what you need to do, and I'll continue the lecture because right now I'm safe. Okay, so thanks Elise, we'll put this online soon. Okay guys, Sierra, maybe you can monitor that it hasn't taken out my house, because my house is at the bottom of Mountain Lake. Okay, let's continue. So, this is the only thing we need to be true. Now, there was a question earlier on in class when I was talking about MLEs, and I think there was a question about parameters on the boundary of the space, so on and so forth, what happens there, and there may have been some confusion mixing this theory with that. So, okay, our job is basically to prove that this is true. So, I'm going to tell you a couple facts. We're going to keep this in mind. This assumption needs to hold all over the place. So we're going to need this assumption and we're going to use it. You'll see exactly where we use it. But I want to tell you a couple facts. Fact one is the expectation of the derivative of the log likelihood, if you will, I'm operating on theta, is equal to 0 once I integrate out x. So this is true. And that's true if this assumption holds. So the original assumption needs to hold that I can fly this derivative inside and out. And if that assumption holds, then this is true. And you can prove that to yourself. We'll prove it in just a moment. I also want to point out another fact. That if the assumption holds, so that derivative can be slid over the integration. This denominator term has another expression So I'll write this down, expectation of derivative log, I say likelihood, in this step. Squaring this thing is equivalent to this minus expectation of two derivatives second derivative over the log likelihood. And so if the assumption holds, Fubini's holds, you can prove this directly, and you've probably done it quite a number of times. I'll make a note, prove this to yourself. Here's how you do it. Work out the left-hand side. Just work it out directly, and then work out the right-hand side and see what needs to be true for them to match each other. You will need to apply Fubini's theorem for it to do it. Okay. So this is called the Fisher information. So, Fisher info. Fisher info always exists. It's this thing. I mean, if the covariances and the variances exist, that thing should be finite. And sometimes you can write it down like this. We call that the Fisher information. Specifically, this is the expected Fisher information. Okay, this statement is always true. So there's two things that are true. If the assumption holds, we'll go through that. We'll at least prove this one. And this statement is always true right here. This is called Cauchy-Schwarz. And for those of you that have encountered Cauchy-Schwarz in linear algebra or some other field, this really is the same equation, just being applied a little bit differently. So this is that same statement that they use with inner products. This is how statisticians use that statement. But basically it says that the covariance squared is less than the product of the variances. And we'll look at that as well. So, but these are two statements that we're going to need in proving this. So I'm going to prove something more general to start with, and we're going to get this. So that's where we'll start. So let me try that. So let's begin our proof. And next time, we'll look at examples. Okay, so let's just do some general stuff. So for now, consider some function arbitrary function. And I'm going to call it G. And I can plug my data into G. I can do something with it. Okay. The book's proof gets a little bit confusing to students because they use W in different ways. What I'm going to do instead of the book's proof is I'm going to introduce this new function, and I can plug anything in for this new function, including W. So right now it's just an arbitrary function. Doesn't have any special properties, except that it's differentiable. So I'm going to say the expectation and it's differentiable. So expectation exists. and differentiable. Okay, so maybe not completely arbitrary. I can at least apply my operators as I do in Cramer-Rao. So I can do all that stuff. So I'm going to say we can perform this operation, gx. Okay, I'm allowed to do this, so those are my assumptions. Let's just say we can compute this thing. Okay, I'm going to show you what this is equal to. Integral gx with respect to its sampling distribution. So my expectations all mean the same thing in this lecture. They're always being taken with respect to this distribution. And I'm going to invoke my assumption. So my assumption, where I can slide this over here, I'm going to apply. So assumption, this thing is equal to the integral of the derivative of fx given theta dx, by definition. And I applied the assumption that I slid that derivative across. So we've just used our assumption already. So have to be able to do this. And I'm going to multiply by a funny form of 1. So gx, derivative with respect to theta, fx, given theta, over fx, given theta, times fx, given theta, dx. So all I did is I multiplied and I divided by fx given theta. So same equation. And I'm going to reinterpret this. I'm going to write this down as the expectation it is. This is an expectation of this creature, right here. So I've rewritten the expectation effectively. So this is expectation of gx, derivative, fx, given theta, over fx, given theta. Just keep in mind, this derivative is acting on that. So there's no cancellation right there. And that's what it is. So this is equal to that, right here. I'm going to reinterpret this one more time, and I'm going to write this down like this. Expectation, gx, derivative, d theta, logarithm. This is the natural log. These are the same things. When I apply this derivative, I get 1 over the function inside, and then I apply the chain rule, which gives me this back. So when I take this derivative over the log of that function, I get this. They're exactly the same things. And so we just proved something. And we're going to use this fact over and over and over again. So this is important. We're going to recycle this statement all over the place. This is equal to the expectation of gx log of the derivative in first. Derivative of the logarithm of the fx given theta
All clear notification.
Looks like the tornado is all clear. Sierra will keep us posted. Okay, so this is what we proved. We're going to save that fact. What we inadvertently just proved by doing this is that this is true. So we've proved this fact right here by proving this more general statement. So I can take the expectation over G, I can take derivatives over that, and I can apply my assumption that the derivative slides around. So I did use my assumption in proving this. So this tells us this is true. If we let gx be equal to 1, this is a little bit of the confusion I usually see when people read through the Casella and Berger proof, is they change the definition of the estimator that they're using, and we're avoiding doing that. This arbitrary function that I'm kind of talking about that has some properties, I can take an expectation, I can take a derivative, this constant function satisfies all that. So if I let gx be equal to 1, then I just showed that the derivative of the expectation of 1 is equal to something. I know one thing it's equal to. I know that it's equal to 0. Because the expectation of 1 is just 1. The derivative with respect to theta of 1 is 0. So it's 0, but I have another name for it. I can write it down like this. This is going to be the expectation of 1 times the derivative of the log function. So if I can slide my derivative over the expectation operator, i.e. Fubini's is valid, then this function right here, which I'll get rid of that 1, is equal to 0. Sorry, this is 0, not theta. So just be clear, this thing is 0. That's this. We will recycle that a few times. So every time we see that, we're going to replace it with 0, and it pops up several times. So that's something we know. So I'm going to leave this fact here. It's something we've proved. Let me try to convince you of Cauchy-Schwarz. You probably know that this is true. Switching to Cauchy-Schwarz. And then we'll apply Cauchy-Schwarz and rewrite it. Cauchy-Schwarz comes from this. This is my pseudo-proof. I'm going to take something you probably already know. That the covariance of any two random variables, I don't care what these things are, they're both random variables, and maybe they're associated with each other. The covariance over the square root of the variance of x divided by the square root of the variance of y has a name. And if you've taken any stat class, including in high school, you know what this thing is. This is the correlation coefficient. Interesting fact that you can prove to yourself, that if you have any two random variables and you standardize them, i.e. you subtract off the mean and you divide by the standard error, and you take the covariance of that thing, that's also the correlation coefficient, and it's equivalent to this. So this is a standardization form that we often use. This number right here lives between -1 and 1. So I didn't prove anything. You already know this. And this measures linear relationships. Okay, so correlation coefficient. From that, if you know what correlation is, and you've already convinced yourself of this, then you already knew Cauchy-Schwarz. So the difference between this and that is simply squaring both sides, which I can do. And so, from squaring both sides, we get this statement. So we've just proved that. Keep in mind that's squared right there, and it got rid of the square roots. Down below, I just knew that the square of this thing, because it's bounded between modulus 1, squaring it always makes it positive, that now I have this statement. Okay, let's apply everything we know. From that, we're going to get the Cramer-Rao lower bound. Applying Cauchy-Schwarz, and I'll apply it to our estimator. And the derivative log fx given theta. So Cauchy-Schwarz was this statement about two random variables. They might have been associated. Here are mine. So I'm going to apply this to that statement. And so let's just write this down. Covariance between Wx and this thing is going to be bounded by variance statements. Direct application of Cauchy-Schwarz. We're going to rearrange terms, and we're going to see what this thing is all about. So let's just keep in mind, we know what this is bounded by, right here. So we know what everything is bounded by. Just rewrite. It's going to be a statement about the covariance. So I'm going to rewrite the covariance real quickly. The covariance is equal to the expectation of Wx times derivative logarithm fx given theta minus, so I'll just remind you, this part that I'm writing down is just the covariance. And then I'll end up writing my bound over here. Just 1 second. Minus the expectation of Wx times the expectation of derivative log fx given theta. That's covariance. This thing is bounded by this still. Variance of wx. Write that meter. What I'm going to do right here is I'm going to divide by this term right over here. So this is the variance d theta log fx given theta. Okay. I'm going to rewrite the denominator, but what we have right here is this thing in the numerator. I'll help you out real quickly. I did squish this in here, but I know another name for that. That's sitting right here. That's 0. And so this whole term cancels right here. This looks a little different. If I write it in terms of expectations, so the variance I can always write down in terms of expectations. This is going to be whatever this random variable is, fx given theta squared minus expectation of derivative log fx given theta squared. And I know a name for that as well. That's 0. So let me just write down again everything we just showed. So we just showed this. Expectation of wx, derivative log fx given theta divided by the expectation d theta log fx given theta squared is less than variance of wx. So we've just shown this. Our first step of all of this was to show that this had a different name. In step 1, we showed this thing was equivalent to the derivative, so long as the assumption applied. So the assumption is used in both the numerator and the denominator here. Expectation wx squared. This thing right here. So we already had a different name for that. Oh, and I made a mistake. All of this up in the top right here was squared. That was this square. So if you just wonder where I just got that square from, it should have been right here. So Sierra was dying to tell me that.
No, I forgot that too.
So sometimes things magically reappear if you've done the proof a couple times. So this proof is in your book. It's written down just a little bit differently. But this is what we set out to prove. We used our assumption. Every line of our proof used our assumption. We recycled this about 3 times throughout everything. This is a general fact, so long as the assumption holds, Fubini's holds. we're going to come back around and we're going to look at this statement, go through a plethora of different examples, and try to give you some intuition for why this is true. But this is extremely useful. We're not going to go explicitly through the attainment theorem, but I think we can talk about the condition briefly. So usually I just say, compute the left hand and the right hand sides. If you've attained it, that's probably pretty good. That's usually what happens. Sometimes you can't attain it and you want to know if it's even possible. And so the proof has a lot of insight on how to develop estimators as well. So I think that's it for now, you guys. We're going to switch over to Zoom in just a moment. Thanks a lot.